Welcome, everyone. This is the last of our 10 series in the spring of 2020. And the topic this morning is big batteries for intermittent energy. And I picked this topic and asked for volunteers, and Lou Hanisch kindly volunteered. And I appreciate that because it takes a bit of work to do this. And I know you've put a lot into it. The reason I was interested in this talk is that we're all getting pretty familiar with small batteries in our cell phones and various things around the house. And they're very practical and generally pretty safe, not very expensive. But the big batteries for intermittent energy are a challenge because to have sustained energy stored for a period of time, given our fascination with wind and solar, it would require fairly expensive and novel technology to provide this energy over a period of time. And I think Lou has covered that complex subject very well in what I've seen from his handouts. Lou, by the way, I should tell you, I got his master's degree in 1974. He taught high school full-time and community college part-time in biology and physical science for 18 years, and then went to the Argonne lab where he developed and implemented programs for junior high and high school teachers and students for 27 years. His thing that he enjoys looking back the most is developing for more senior students, ages 16 to 18, X-ray beam time at Argonne's Advanced Photon Source in order to expedite their independent research projects. And I'm sure that was a lot of fun and satisfying for you, Lou. And I appreciate very much your willingness to get together on this final session of Pathways to a Sustainable Planet. And at the end of your talk, when we've answered all the questions, I'd like to come back on and tell you a little bit about what I'm hoping we can achieve this fall. So you have the floor, and thank you in anticipation of your seminar.
Well, thank you very much, Richard, for that wonderful introduction. We're going to move into this very quickly. Just to say, battery has a very broad meaning here. It's not all redox batteries or electrochemical. It's going to have a wide range of things. And what I see, if you can see the first screen, there are many levels of batteries that can work on the grid, from residential all the way up to grid bulk storage, which are huge facilities. There are some of those. I also would like to encourage you, if you haven't seen the world's biggest battery video on the resource sheet at some point, to watch that. It's just a fun thing. I was trying to bring it up here, but I'm going to skip it. It's probably not going to work. So with this in mind, we're going to move into the first slide, and we see a large land turbine by Siemens. It's 4 megawatts of power, and a woman is filling up the gas tank of her vehicle, pumping 2 gallons per minute. My question is, which of these would have the most highest rate of energy flow? I'm going to say that broadly, and it's kind of a rhetorical question because we don't have a lot of time to let you think about it. And that would be the woman. She's well over, she's like at 4.4 megawatts of power that's actually moving from the gas tank underground to her car. Now that's a slow pump. I mean, you could almost double that rate, so she could be almost double the power of this big land wind turbine that you see. So what that tells us is petroleum really spoiled us. It gives us a tremendous amount of energy. We can store it. It's stable. It doesn't disappear on us. And we can convert it intermittently to the power that we need in whatever we want to run, if it's a vehicle, a pump, compressor, some other device. And we can make it in excess, okay, and store it. It's really has its own built-in energy storage. So this is one of my favorite slides. It's showing on the x-axis the amount of in the kilograms or the mass, and on the y-axis the volume. And we see batteries way down here, and we see gasoline way up here. Jet fuel and diesel would be above that. The hydrogen is sort of in the middle, but you know, batteries don't have the density that, even though they're dense in terms of a lot of ways with storage, they just don't have it with liquid petroleum fuels. I mean, so this is something, I'm not touting this. We have to get away from this. We know this is hurting our environment. So we have to find some other ways of working electricity. And the big thing we have to remember, and we've heard this in many other presentations, that the electrical system works by supply and demand, production and consumption, and it has to match every moment. You cannot have one out of sync from the other. It just doesn't work. It's remarkable that you flip on a switch and somehow we fire up some device at home and it stays in sync. And it's just remarkable how the grid operators make that work. So, and we're doing it without very much stored electricity, okay? We're just somehow making it work. It seems magical. So, but that, when, like Richard indicated, as you start to bring in renewable energy, this gets a little more, this gets dicey. It's harder to do. And we want to stretch this timeline, and we want to energize these electrons. And can we put them in a bottle, so to speak, like a genie in the bottle? Well, in one form of storage, you can do that, but that's not what I'm going to talk about. Supercapacitors can do that, but they don't really help very much. They don't have very much energy, and they have a lot of downsides, but you will see a little bit about those. The one thing that we have to do is the second bullet, and that's we want to take a variety of technologies that collect energy or electricity at one point in time, change it to some form that we can store, and then change it back to electricity later when it's most valuable. And this is key, when it's most valuable. Every time you have an energy conversion, you will lose some of that energy. Laws of thermodynamics. So there's two, you're going to have two of these every time you're trying to go through a cycle, a minimum of two, when you want to store energy, okay? So now, so with that in mind, we're going to move on. This is shows the erratic nature of wind on land over the course of, I mean, this is very hard for the grid to deal with. It would be so much easier if we could even this out. But again, this is on land. It's not offshore wind. Offshore is much more even than this, okay? And whether it's 2012 or 2022, I mean, this is pretty much how it would work in North Dakota in January, okay? Here's one of solar, and it's peaking. This is a bar graph. It's peaking in June, July, and August. That's our peaks here. Whereas, and we would like to even that out too in some way, but we're really more concerned about 24-hour evening out. But what I wanted to show you with this, here is wind, very erratic, and its low point is in July and August, whereas with solar, the high point is in July and August. So they're kind of complementary in some ways over the course of a season. But this stuff's got to get evened out, and this is kind of what we're going to do with. Here's another graph just to show you the growth of renewables quickly.
Could I ask you a quick question?
Yeah.
Could you go back to that last slide for a second? That I find that fascinating on the left. The fact that the curves became more
erratic.
variable with time. Do you think that might, although you're only looking at a 3-year period there, but do you think that might be consistent with climate change, with the volatility of wind?
It's possible, Richard. I'm thinking the number of installations were low here. The installations kept going up, and with more installations, it might have made it more erratic as well.
That meso, as I understand it, extends from the border of Canada to the Gulf of Mexico. So it's the windiest part of the entire continent. So you're pooling a lot of data there. And I find, although it's tempting, you're only looking at a 7-year change, but 3-year change.
3 or 4.
But it's still intriguing to me that I would love to see that graph extend over a 10-year period.
Right. And I've tried to find that and I can't. Yes. This is an older slide I had.
If you ever hear more about that, I'd be very interested. But anyway, sorry to interrupt you, but that was a fun slide.
Yeah. Well, anyway, it's showing the erratic.
There was a raised hand. I just want to make sure you gentlemen saw that somebody has a question in the chat.
Oh, very good point. Thank you. I sometimes overlook that. Let's see what Bill. Oh, he asked what is meso, and I just defined it, so that's okay.
Okay, very good.
Stands for Midwest. I've forgotten what it stands for.
I'm glad you knew that because I didn't know that. All right, okay.
But anyway, it's in the middle of the country, and it's a huge grid. It excludes only Texas, which is the windiest state, they say, but they've got their own special grid.
Okay, we're just showing, this is December of 2021. So this green graph is very recent, just a few months old, but it's showing renewables growing. Actually, renewables are including hydro. So if you stack all these 3 up, it will equal this, and the remaining ones stay the same over on the other graph. Anyway, it is growing, and that's just what's happening. I mean, so I'm just mentioning that. Battery storage, look, that's growing too. And this is all forms of batteries from residential up to grid bulk level. And they went up in the last three years before this year, 7-fold. Okay. So this stuff is growing like crazy, and where it'll be in 2022, it'll be way up there, and who knows where. This graph on this side, if you can see it, is the red is showing the capacity that was added just in the last year. And California, Texas, Florida, they're way up there. They should be up there. Nevada should be up there. But this is not including residential or commercial. It's just including utility and bulk level or grid level. I don't see Wisconsin on here. Where is it? I'm not seeing it. All right, this will change too. Okay, now here's a graph that you guys all know. I'm going to just mention a couple of things about this, that we are on the same page. We have on this left side, we have base load 24/7, 365. It does not necessarily mean it's full power all the time. That gets in the load following, and I want to park this one for a while and just mention these percentages are percents in the US that are pretty current. And fission has held 20% for quite a while, actually. Coal should be decreasing. Natural gas has probably picked up and taken up the coal. On the discontinuous or intermittent side, you have wind, which is quite a bit higher than solar. I don't know when they're ever going to equalize, but you have land versus offshore. I don't know if you can see the offshore. That, by the way, offshore is more continuous. Those turbines are very high. They run more steady and with more force. And some people think of offshore as sort of in between these two areas. But then we have peaker natural gas plants, which just run at peak times to take, add the extra power that we need when we're headed home and turning everything on and our AC is blasting like crazy. We need those plants, but that's kind of, those are natural gas pretty much right at the moment. Petroleum, biofuels, and we're blocked out. I don't see the percent there. But I don't know if I can pull this off, if that shows it. 2.1, it's not very much, okay? And tidal and wave has not been developed, just like fusion has not. But my question is, between these two, where does pumped hydro belong? And it's going to be rhetorical because I'm going to just kind of give you just a couple seconds to think about it. And you might say, well, pumped hydro is discontinuous, it belongs here. Well, might think that, but both of these are linear. In other words, you change you convert energy to electricity, and it goes out on the grid all over, and it does work and it does things for us, and it ends. Okay, it's linear. Pumped hydro is cyclic, but what I was saying here, you can power pumped hydro with both of these boxes. When that little subset does that, it's cyclic too. But for the most part, these two are linear. And pumped hydro is a form of energy storage. All storage is cyclic, right? I just want to make that point. Okay. Oh, I got to get back into the slideshow. Here we go. Here's a concept. I'm going to move into some grid stuff so you see things out on the grid. This is in science, we often take something simple to understand it really well and then apply it to something more complicated. And this is a microgrid. These do exist in Alaska, Puerto Rico, Haiti in some fashion. They're not going to be this extensive. And Richard talked about diesel generation. We know hospitals and other places in our country have backup diesel. That's not one of them. This is running their whole grid. It doesn't run all the time. Runs just for a little while maybe, and it's expensive. The cost per kilowatt hour to run this is very high. What would be better would be to take a modular fission reactor and replace that, even if it's a small one or something within this range, and replace this thing. Or hydro isn't available. I have some other examples up there, but
quick question.
Sure.
What you just said applies very much to Hawaii. Hawaii has been using diesel generation for the longest time because they don't have very much solar, and they're not interested in looking at offshore wind, and there's no projection for them to get modular fission reactors anytime soon. But I hope somebody convinces them, because that would be a natural for Hawaii.
They need it. They need it. And Puerto Rico has some of these, but in a lot of the island states use this kind of a thing. Okay, so this is a small scale. I'm going to move up to the next slide, which is larger, and we have a coal plant, and this plant is about on its last leg. So we're going to replace this with an atrium reactor, by the way, and that's happening in Wyoming. We have a substation that's going to change current for voltage and send energy down transmission lines. And we have, I don't know if you can see there's a windmill, but that's renewable energy. Then we have another substation which changes the energy into a form that these users, whether it's a factory or hospital or whatever, big box stores, can put solar on their roof and stuff like that. And then we have a residential community here. Okay, so this is sort of a larger grid in a microcosm. You'd need many of these to make up a full grid. But what's interesting is there's all these levels of storage can occur in here. Usually bulk or grid level is where you make the energy, whether it's renewable or sometimes even fission. They will, or gas, they'll have a big facility. It's huge. And then we go into utility level here, which provides some backup, and then for maybe hospitals and other facilities that are important, government. And then so the rooftop solar on the big box stores and the buildings that make up industrial parks and things, they could use a commercial storage. You'd have multiples of these. And then finally, residential storage is down here. I just wanted you to get a visual of this so you could see. And these are all, again, substations of different types that are changing the energy so you can use it for the end user can use it. I'm gonna, yeah.
Sorry to be barging in with the questions, but why would you have to have so much storage if the grid itself is functioning? It's not a true storage, you're right, but it seems to me that the main reason for bulk storage in this kind of a system would be where people want to use energy at off times. They pay less for their electricity in the middle of the night or on the weekends.
Well,
and so I'm wondering if that's why you have so many opportunities for storage on this slide. Is it financial?
well, I think so, and that's true. You would have off-peak
Okay.
that they can tap, and that's true for here too.
Yeah.
That's my next slide, is to talk about what
Sorry.
this is. But here you have these big buildings. Why not have rooftop solar on them? I mean, it's a footprint that could be utilized.
Absolutely.
Okay, so so power residential are these guys, these Powerwall 2s. They're lithium ion. They can discharge for about 4 hours. This home has 3. It's a large home. But what's kind of neat about having 3 is you could, for peak periods, you could kick this one on first, hour later, kick this one on, and an hour later, kick this on, and you could stretch your peak period out if you needed to, or provide more energy during that time to run more things, either way. This one that you see over here is, I don't know if I can bring this back, zinc bromide Primus power. It's a commercial unit. It is a flow battery. This is lithium ion, this is flow. They're not the same, but they would only last for about 4 hours each one, okay? And that's it. That's all they're gonna run. All right, so now we wanna get into the duck curve, and this has been brought up before. There is a great video on this that's short. It's like 3 minutes, and it explains everything I'm gonna explain, maybe even better. But basically, this is like a small area in California, maybe a county or 2 or something, where California had incentives to put rooftop solar up back in maybe 2010 or soon after Obama was elected, and they started putting more and more up each year in these areas, and basically you've got this curve of time of day on the x-axis, and you've got the power that's required on the y, and what this did is it just lowered the red curve that you see here. It just got lower and lower because the demand wasn't needed. They were getting their energy off the solar panels, and they didn't need the demand from the, and now this black line represents like baseload power. If the utility had an agreement with a fission plant or something, we want to keep that power in there. And what happens if that's competing with the rooftop solar? Guess who's going to win? The fission, because the rooftop solar is going to get decoupled. So wherever you see this area here, where the belly is below the line, you can't use the power. It's called curtailment. And if you could export the power, that'd be fine, but that may not be reasonable. But what the solution that did solve this part of the curve is storage. And that was if 1/5 or 20% of the households had the Tesla Powerwall 2s, these guys going, you know, you would get the blue curve, and that would, you know, that really would help things out here. The problem is the head, which I can't see here. The head actually gets helped as well because this red curve gets really high, and that's like a peaker period from 5 o'clock through maybe 10 at night, and you have to add, the grid has to add more energy to accommodate that. But with the storage, that amount of energy decreases. So in essence, this is what the duck curve, I mean, hopefully that makes sense, that storage really helped out with this curve. I mean, I'm going to refer back to this again in just a little bit, but I'm going to move on. And again, there's a great video. Let's get my slide presentation going. There's a great video on the duck curve. You should watch it. Does a great job, although it pushes renewables a little too much. So we covered this first item somewhat, integrating renewables into the grid. And this second one is called load following, and that's where you have some of your base load plants working at 100% or 98%, whatever. And then you have a subset of your base load plants cutting back their power a little bit, probably to accommodate renewables, but to also balance things. What happens with load following, and I don't know what percentage this would be, these graphs may not be reflecting how much load following actually occurs with certain power plants, but I like this graph in some ways a little bit better because it shows, for one thing, it shows storage happening here, and when you have storage here, you're reducing the amount of load following. I mean, it minimizes load following. It doesn't have to cut back as much, and you can use this energy then during peaker periods. You don't need peaker plants, gas plants that just run for 5 hours and that's all they run. I mean, it's kind of a waste. So load following is a great thing for balancing the grid and sort of allowing different sources to come in and work together. I'm going to back up to, with that concept in mind, let's go back to the duck curve. See, there was no load following here. And because of energy storage in the blue line, we eliminated curtailment. Curtailment didn't occur. But if there wasn't this much storage going on, load following would have to dip or else you'd have curtailment. And that renewable energy, the solar energy, would just go to waste. It would be decoupled. Okay, so the other thing that makes a lot of sense is number 4, is just with energy storage, you have a lot of ability to just fine tune the grid. You can pull from a battery here or there that are complex and make things work a lot easier. But hopefully that's very intuitive, I would think. I'm not going to say too much more about that. Number 5 is really important because this is going on now. We need to have available energy in a distributed way, not just at a power plant. When the power lines are down, that doesn't do you any good. You need it distributed. And so you need those different levels of storage to help deal with all these severe weathers that we've been having, tornadoes, hurricanes, you name it. Then, and the flooding that comes from that causes a lot of damage. Then you have droughts which cause wildfires. We've been hearing about those constantly. They're not going away. So if you have You need to run pumps to get rid of flood water. You need to have that energy there in a distributed way. And that's going to take a lot of fine tuning to do that. Okay. Just to illustrate a couple, so if you don't do it, you have brownouts or blackouts, right? And California's had plenty of those, but we had a real big blackout in 2003 in New York and Toronto area. And that was a software issue that screwed up. It was a couple limbs that hit a power line that shouldn't have done anything, and it cascaded out of control because the software didn't work. Think about August of 2017, Hurricane Harvey dumped 60 inches of rain in this area, Southeast Texas. And guess what else is out there besides a lot of people, is chemical plants, the refineries, all of these things. They couldn't finish some of their processes. They're releasing plumes of toxic materials, and they just didn't have enough stored energy right near the plant to pump out water, to do this, to finish things up, so they wouldn't have these premature releases. So that, this is important. There's a lot of ramifications with not having the power you need when you need it. And then this last thing was a 60-minute piece. There's 5,500 substations in the US. If 9 strategic ones go out, much of the grid could go down. This was in 60 Minutes about 7 weeks ago. There was some expert who made this statement. I don't know how correct it is, but we do know that some of the substations have been attacked, shot at, and different things. And of course, software could be another way to attack them. So we have to have extra energy to maybe bail them out if something happens like that. Okay. I'm going to move through this list really quickly. This is a characteristics of an ideal energy storage system. And that is, there's only 8. You could probably add some more. High efficiency, I'm 60% is okay, but boy, 99%, which is lithium ion, that's really great. Long duration, at least 4 hours, extending to 12 hours, some into weeks if needed. That way it will be rare. This is a ballpark output that you might need, and you could have multiples to extend this. And this is a energy capacity in gigawatt hours. I mean, over a 24-hour period. These are, again, ballpark things. So when you get them big, the larger facilities would be in this area. Smaller ones, like commercial, would be even below this maybe. Cycles, 20,000 cycles at least, and lifespan 10 to 40 years. Lithium ion only lasts 10 years. That's it. And it's done. Scalable, flexible, you can make multiples of a lot of these things to make them scaled up. Viable, there's 2 types of economics. One, to install the technology, and the other to run it, operate it. And this is more of an operational, like less than 30 cents per kilowatt hour. If it gets more than that, then it's kind of pointless. You want to have it. I've heard some as low as 5 cents per kilowatt hour for storage. We'll see how that plays out. And then a low environmental impact. Okay. And we know that pumped hydro is not that. That's one of the faults of pumped hydro, unless there's a natural lake or something somewhere. So weight and size are irrelevant when you have stationary energy storage. It's just, you don't have to worry about it like you do on a vehicle. Okay, so we'll sort of tie into some of these. This is a real busy slide. I'm not going to spend much time on this.
Would you be ripe for some questions at this point?
Yeah, we should maybe take a break on. We got a few building up. absolutely.
After this slide or now?
Well, just to mention, we can finish it
Okay.
now that it's there.
Okay,
Uh,
fine.
so coal and nuclear would use this system, which is a steam turbine generation, steam turbine generator system. Okay, and coal would be burning, would be combusting. Nuclear would not. So nuclear doesn't need a stack. Nuclear uses this cooling tower to actually add more efficiency to the system by cooling this recycled H2O back into the boiler. Okay, so this is something that is out there, and it's scaled very, very large. These are huge turbines. They have to be to make them the process efficient, extract enough energy. This is the motor, by the way, back here that the turbine is turning. Okay, this side is more direct. Wind turbine, you know, it's turning a shaft. Everything has to turn a shaft, right? And it bumps up the RPMs and turns a generator. Water turbine doesn't have it, just designed to turn have the water turn at the speed it needs. And then this is a natural gas. So you have a generator, compressor, turbine, and the combustion chamber for the gases here that creates reactants that stream out with tremendous kinetic energy and turn the turbine like a jet engine. But guess what? There's a lot of heat left. And so, but it is turning this generator. All right. But this heat will go up to this stage up here. You have what we call a combined cycle, which is this plus this, and that makes natural gas very efficient, like it or not. Okay. So I'm going to stop with that because that's enough to understand this stuff. But you will see these different types of turbines, and I'm not even showing you all the kinds that water have. I mean, there's a lot of them there. So we're going to stop with that.
But you have more slides to show us after these questions?
Yeah, now we're going to get into actually the storage, the 11 storage.
Okay,
and we
fine.
can do questions if
Good. All right. If you want, you could read them directly, or I could read them to you.
well you go ahead, Richard.
Let me read them. Bill Temick asks, if you were to look at slide 7 again, you would see that there are times when both wind and solar are low, such as winter. And this has big implications for storage.
Okay.
Just a comment, I think. Lee asks, what size defines the system as microgrid? Do you have an answer for that?
Not really. It's just it has those pieces. I think the energy output, the power output might define it. So it's not going to be much above 50 megawatts or 100 megawatts or something in there.
I would think
Yeah.
that's reasonable.
Yeah.
George Erickson, to everyone, says painting your roof white is superior to photovoltaic for environmental and global reasons. These panels get hot. And what I think he's saying is that there's heat released from those solar panels. So in large quantities, you could increase heat with the solar panels, and it might be just as good. George makes the point, perhaps better, if you just painted your roof white. You wouldn't get so much energy, but you wouldn't be releasing, personally, you wouldn't be getting energy, but you'd be contributing less heat to the environment around your house.
Okay.
Lee makes a comment, rolling outages in California happen because they got rid of too much of their capacity. They decommissioned all their coal plants but one, and all nuclear plants but one. And so they're prime because that base load has been removed. That's contributing to the rolling outages in the grid.
Right. No, I think that's correct.
Yeah, I think so too.
Over there. And we've had that come up before in other presentations. I remember.
George asked a question, why do you exclude nuclear from image number 2? The energy stored in the nucleus of thorium or uranium atoms is about 1,000,000 times greater than an equal volume of any other fuel source. We have enough uranium and thorium to last for at least 100,000 years. I agree with the point, George. I think Lou is simply using what's in common use today. Isn't that right, Lou?
Yeah, is this slide 2?
I
I'm
should
not
say
sure what
image
the
number
image is.
2, I'm not sure. But I know you did have some slides back there where you showed coal and gas and
Yeah.
not necessarily nuclear.
No,
but that's not
nuclear
excluded.
would be off the charts. It was more about liquid fuels and
Yeah.
things that were more
So there was
germane.
no intention of
No,
excluding
not,
nuclear.
it
It
would,
was more historical reasons. Okay.
yeah, absolutely.
Another question from Bill Timmick. What is the potential for large volume liquid metal energy storage associated with fission?
Oh, we'll kind of get into that a little
I
bit.
think so.
And
Yeah.
further slides
That
will touch base on.
sounds like
Yeah.
the Natrium system that Bill Gates is doing.
Yeah, right. Except they're using
They're
molten
using
salt.
liquid salt, right? Molten
Yeah.
salt.
Yeah.
Unless he's thinking, Bill may be thinking a little bit of liquid sodium when he says liquid metal, but that's not so much storage, it's energy generation. Anyway, we might come back to that. George says to everyone, Pacific Corp, which owns 13 wind farms, has sued the US Interior Department to keep it from revealing how many birds and bats their windmills have killed. I've heard of a good bit of litigation. Apparently, a lot of golden eagles are being killed also. And that's really a shame.
It is.
As well as bats.
It's not what
So
you want.
those lawsuits are definitely in progress. Steve Shellen asks or comments to everyone, if you have power lines down, you do not want power on the lines for safety. Thus, local power needs must have local power generation. And I think the ultimate solution to the high windstorms such as in Texas is that if you don't have those lines buried, you leave the public vulnerable. And I think the nuclear plants in Texas did shut down their energy for a while until they got those lines at least lifted or covered, if I recall.
But
you agree with that, Lou?
Yeah, and but my point, I agree with everything Stephen says. This is why if you had local energy storage, distributed around, you'd have some power to do things. Pump out water, do this, do that, whatever you need to do, and you could tap it in some way. So this is correct. I mean, these storms literally cut us off from the big power plants is what I see them doing when the lines go down.
Yeah.
Anyway,
Okay.
so we're caught up with that.
Yep.
Okay. All right. So we're going to move into 11 types of storage. The first one is land pumped hydro, and these parentheses are indicating the efficiency of a cycle, full cycle. How much, so this is pretty good, actually. It's been around a long time, but my slide is kind of covered up here, but you can see that you need a 300-meter drop from an upper reservoir down to a lower reservoir. And you're going to move water in both directions. When you have an excess of energy, you want to pump it up. When you need the energy for peaker times, you want to have it drive turbines and run down to the lower level. So that's very, this has been around a while. I think it was what first powered the grid in New York State, wasn't it? Was that was hydro, not pumped hydro.
That was run of the river hydro in Niagara Falls. Yeah.
Yeah, but that they're not the same. Okay. So this is energy
they're
storage.
Similar.
They're similar.
But you just don't have to pump it up. It's there all the time.
Yeah, Mother Nature does it for you. Yeah.
Yeah, right.
And Stephen sent me this very interesting thing about Salem, South Carolina, Bad Creek Pumped Hydro Station. Now it pumps about 1 it has energy available for like 1 gigawatt, but it's coupled to 2 other reservoirs either above or below it. So you get this is a lot of energy
Yeah.
that can be stored in these reservoirs and is available, and it can be stored for a while as long as it doesn't evaporate too much, right?
Mhm.
Okay, so the pumped hydro has been around and it's very important. It's just we don't have a lot of places that can replicate it, and that's a problem.
Well, it doesn't get much publicity either.
Yeah,
If Steve hadn't brought that to our attention, who would know about it?
yeah, that's really. I think there's a big facility in West Virginia too. I've
Uh-huh.
come across that has, but though that's the Appalachian Mountain. I mean, you got mountainous areas that are perfect for that kind of thing.
Yeah.
Okay, ocean pumped hydro. Again, this is these devices. First of all, you need offshore wind or coastal wind and excess that they can put into these chambers. These chambers are made out of concrete, reinforced concrete, and they have a turbine or a pump on top, and they're sunk about 700 meters down. For every 10 meters, the atmospheric pressure increases a whole atmosphere. I don't know what that unit is, but
Every 30 feet.
yeah, so that 10 meters would be about that. And so you're increasing the pressure 70 times by putting these down on a shelf here and anchoring them. So that makes the turbine spin that much faster or longer, however you want to regulate that, by sinking them down. Okay, so that's how these pan out. I don't know. We'll see. This is just a concept that's out there. But they got to be connected to the turbines. There's a lot of wiring that has to be done and so forth. Then
So
this
basically you're using oceanic hydro pressure as a substitute for elevation of a lake and gravity.
That's exactly it.
Just
Very
otherwise,
well stated.
Yeah, well, that's a very cool idea. It's going to be really interesting because that could be a great source of energy along coastal areas where there's a suitable shelf.
Yeah, where you well, whatever they have. I mean, if they can only go 500 feet, then or 500 meters, then they go that deep.
Yeah.
Whatever they have. But it's interesting. The other compressed air storage, you have to have a reservoir underground that doesn't leak, and you can just pump air in under pressure with pistons. That creates heat. If you can take that heat away and bring it and hold it and bring it back to when you want to release the air to turn and add that heat to the air, it's going to make it more efficient. And vice versa. When you, I don't know if you can see my duster here, but if I press this button on my computer key duster, this gets really cold really quick. You can get frostbite. And when you let air expand, it's going to, there's a cold generated, and if you can bring that cold to the other side, it makes everything more efficient. So this is about maybe 50% compressed air, but it's a huge area and could contain a lot of energy stored. The other thing that one of the videos that I gave you on the sheet, they do water in the same way. They find fracking reservoirs that are tight and pump water under pressure, and then they bring the water back out. So that functions pretty much like pumped hydro, but you're going into the ground. You're going downward, not upward. Okay, you're reversing everything. There is a video on that. I think it's from Texas somewhere, QuidNet. All right, so that's 3 of these. We got a few more to go. There's a mechanical system. This is called Energy Vault. Wikipedia says it's 90% efficient. So what they're doing is when there's excess energy, they're stacking, they're taking these blocks and moving them up to this state with a bunch of these booms. And you can, they're cables, and they're, in other words, there are motors that have to lift them up, and that's stored energy by potential energy by the height of the block above the surface. And then when you want to release it, you drop these down, and that's a form of stored energy. They hold a moderate amount of energy. They're very tall. I wouldn't, but they're getting a lot of criticism because first of all, the cables get blown by the wind, and how do you precisely move them into position, whether on top or whether on the bottom? They're susceptible to wind, so they're kind of redesigning this whole thing. But it's one of these ideas that's out there. The other problem is this is concrete, and it's going to have a high CO2 equivalency, making it, you know, and there's steel and concrete in here. And the other problem I have with it is how friction free are all these cables and pulleys and everything in the system? I don't know. I think this 90% is a little exaggerated. But one thing that is very good is flywheels. They're much smaller. They don't hold near the energy as this energy vault system, but they spin at very high RPM, and they can be efficient because you pump the air out of this chamber and you put them on magnetic bearings, which align them and keep the friction off. And but they don't hold a lot of energy. So if you want to pull energy out, the RPMs drop down. If you want to add energy, the motor up here spins them faster. So the motor generator is the same device. It's going to go in both directions. But these are often with other forms of storage. They're, you know, there's not going to be a big scaled up thing. It's not going to happen. Finally, we get to batteries, and the first one on the list, of course, is lithium ion. Lithium X could be lithium phosphate or lithium phosphorus or some combination of lithium with something else. They could have lithium air, but that's a real hard one to solve, or zinc air. Where you would use the oxygen in the air as one of the anodes or whatever, and they only go for 4 hours. They last for 10 years, and there are heat issues because they can heat up. But the energy is stored in the electrode. And the electrode, there's an electrolyte that lithium can move back and forth. If you discharge it, it moves this way, releasing energy up here for a load. And then it's pulled over here. And the cathode is where you need the cobalt, nickel, or manganese, or all of them, to help organize the lithium the right way. So it can keep the cycle going. You can add energy and push it the other way. So the energy is stored in the electrode. But there are heat issues, and you got to be, especially with a grid, you're putting so many of these together, you have to allow for cooling and separation and all this kind of thing. And the other problem with this is these really work well for vehicles, and you don't want to have batteries competing with vehicles. If you can go to these other forms of battery storage, do it, because you want to save the lithium for the vehicles, right?
Little comment there.
Yeah.
Lee is the ideal person listening to this to comment too, but I noticed when I compared driving an electric vehicle, pure electric, with a hybrid, that I feel much more drag when I take my foot off the accelerator. And so much drag that if you anticipate a red light with any degree of caution at all, you end up not having to use your brakes because you're harvesting all that mechanical energy back into the battery, and you can see your battery charging
Mhm.
as you're slowing down for a red light. You don't get
Absolutely.
that quite so much in a hybrid vehicle because there's not, I don't think, as much regen with a
Yeah.
hybrid. They don't need it so much, perhaps. But sometime we could get Lee to talk to us more about the pure electric vehicle. We hear a good bit of criticism in Wisconsin that hybrids are just as good as electric vehicles because our electricity is so dirty. But I think Lee could make a point that most electric vehicles today, pure electrics, have a very nice regen feature, and it fits perfectly with your diagram there of the lithium-ion battery.
Right. And I have a hybrid, and
There you
I
go.
don't see it breaking, slowing down as much as you're saying.
Yep.
And so anyway, that's an interesting sidebar.
Yep.
So basically, these and you know, there's issues with mining lithium and all that. I don't want to get into that. There's some environmental things with cobalt, and then they may get rid of cobalt and nickel in these cathodes at some point. Who knows? You just don't know where it's going to go.
Right.
Redox flow, and they take the battery inside out. The electrolyte here becomes huge, and that's where the energy is stored. And we do still have this chamber where the two electrodes exist, and ions will have to move back and forth. But the storage is really in the analyte catholyte, which are the electrolytes, and they can be scaled way up, and they're much cheaper. There's vanadium is one of the big ones now, but it's getting in short supply. I'm not sure it's going to compete with some of these others over time. Iron, there's a company called ESS that's developing this iron. It's like, I think it's like iron and rust. It goes back and forth between iron oxide and pure iron, and in this charged and discharged state. But they have to have all these pumps running. There are pumps that push the electrolyte through this chamber in the middle, and that chamber determines the power. How much area you have in there is you can adjust the power. But if you want to have store more energy, just get bigger tanks or more of them, and then you can store it. So the zinc bromide is this Primus power battery. There is a great video on this called energy storage beyond lithium. On my resource sheet, you should watch it. It's about 14 minutes, but it gets into all of this stuff a little bit more. This one, I know Argon's been doing some work on metal organic, trying to find polymers that work with metals and so forth to extend the, you know, the battery, the efficiency or whatever, and make them cheaper. But anyway, so that, and I'm not going to go through these reactions. If you get my slides, you can look at them or find this on the internet, whatever. Then this last one is electro refining. This is a company called Ambry. The problem is you got to keep the temperature in all phases at 500 degrees Celsius. That's a lot of heat that has to be applied all the time. And this guy you'll see all over on the videos, Don Sataway. And he's interesting, but I'm not sure. I don't hear this taking off anywhere. Maybe it will. We'll see. So there's one more electrochemical one, and that is hydrogen. And this one is getting legs. Green hydrogen is going berserk from what I'm seeing. They have a new electrolyzer that is over here. This is the kind of electrolysis that our teachers would show us in school, maybe with an upside down electrode of carbon or something with a test tube. But these have advanced to this, and there's some structure in here, a capillary structure that makes this work so well. Anyway, so the electrolyzers have gotten better. fuel cells is really the preferred way to harvest, turn the energy from hydrogen back into electricity. You could use steam turbine generation if you want, but this would be a lot easier. And this isn't with combustion. There's no combustion here, so combustion only applies to this. And then you got to store the gas, okay? And hydrogen loves to leak. Believe me, it loves to find, it moves so fast at ambient temperatures that it finds any little thing it can leak through. You know, I think this is, and the problem is if you compress it, there's an energy penalty. And if you liquefy it, there's an even greater energy penalty. So you only, if you liquefy it, you only have about 85% of it left, something on that order. And, you know, that you still have to, you got to use it up. It's hard to store for, you know, these filling stations that are going to, if you put it on a vehicle or something, I don't know how those filling stations are going to work, because you got to use it, you know, when you have compressed liquid gases, they have to vent or they'll explode the container that they're stored in. Now, I want to say one more thing about this. This is the reason why there have been vehicles that have been hydrogen powered. Honda made one, Hyundai made one. And they just will never compete with lithium ion. And here's why. You lose 5% at this point, you lose 40% here, and you're going to lose some in storage. You're going to lose half your energy trying to power a vehicle. Why not just power it with lithium ion batteries? You're only losing 5% at all. That's tops. And here you're losing 50%, 10 times. What this might work for is aviation someday. This might work because aviation can't handle the weight of lithium ion. It just can't handle that weight. So anyway, just these, if you don't, I wouldn't invest in any car thing that wants to push hydrogen as a automobile fuel, as a vehicle fuel. It's just too much stacked against it. All right, we're going to move on. This is called the liquid air battery or cryo battery. It's a phase change. Phase change absorbs a lot of energy. And the efficiency is around 60–65%. There's a great video on this. I'm not going to spend too much time. The guy on the sheet, and you should watch it if you haven't. So you have three parts where we have a gas, and we're going to compress it and get rid of heat and get it into a liquid. And the liquid is in the center phase. And then we want to store some of this heat and bring it around to the other side. And again, just like when we want to use this energy in phase 3 and expand it from the liquid to the gas phase, we want that gas really humming. We want that gas flying around like crazy with a lot of KE, kinetic energy. So we're going to add the heat back in on this side after it expands. So that's what these tanks are for. These tanks are holding heat in some form to be used in the last stage, and these are holding cold in some form to be used in the first stage to help liquefy the gas better. And then the middle stage are these tanks. Okay, if that, they actually do it, you see the video, they actually liquefy it here and then they move it. And these are, all these tanks are big thermos bottles with vacuum in between the walls. And all this stuff is available. It's been around in refineries and so forth for years. So it's nothing you have to create. So this company is in Britain, and you know, this might have some possibilities. It's kind of interesting idea. And now we get into the last one, which is thermal capacity technology. And it deals with either heat or cold. Okay, and typically when it's heat, you can run it through a steam turbine generator, 45% of efficiency max, or you could run it through this TPV, thermal voltaic, tongue tied here, thermal photovoltaic cell, okay, which is down here. Let's talk about this one first. STG, this is a concentrated solar energy. These are all mirrors, and they shine light up to this top of this tower where there's molten salt, and the salt melts and holds a lot of energy, and then at an off time, off peak, we can run this through a steam turbine generator, which is down here. Problem is, this facility is died. It's not efficient. There were two, one made in Spain and one made someplace else. None of them are working anymore. They just, there's something wrong, inherently wrong with them. And maybe somebody knows what that is, but it is the concept that I'm trying to illustrate. What actually works better is what the Natrium reactor does. It takes some of the core energy, the heat, through exchangers and melts molten salt and then makes that available. There's a key slide up here that I can't see, but maybe I can see it this way. Not sure I can do that either. Okay, but which shows there's a bump up here, and you can see, you'll see it when you have the slides. Unfortunately, I can't, these are covering them up. But it does, down here, it seems to be load following, and then when you get to this bump on the graph, it does actually adding the energy back into the steam turbine generation. So it's for peak power. It can, it's very flexible. This reactor is quite flexible. So that takes care of. The other thing that's very interesting with heat is you can store it in graphite blocks, which are basically carbon, and it stores quite a bit of heat for quite a long time. This is diagrammatic. This shows the heat, and it shows a metal plate, and when you get it hot enough, it radiates high energy photons over to this thermal photovoltaic heat engine. Okay, it's this thing, it's a cell. It's a centimeter by a centimeter, okay? And this, just recently, they've gotten this to work really, really well at 40% efficiency. And then it creates electricity directly to go on the grid, okay? So, but you've got to have these blocks really hot, and I'm not sure how that all works.
How hot is really hot, do you know?
Somewhere between 1900 C and 2400 C Celsius. So that's 4,300 degrees Fahrenheit.
Yeah, that's why he's using sodium, liquid sodium, because you're getting up there with those temperatures.
Yeah, well, that would be interesting to see how this would work with the natrium. I mean, yeah. But actually, they were using graphite in the video. That you'll see the graphite, but maybe they can do it with some of these other things too. I'm not sure. So this has to be scaled way up to like the surface area of a quarter of a football field. It's got to go way up, and they think they can do it. We'll see how that works. We shall see. We talked about heat. The other thing is cold, and something that you're got to get my slide thing going.
Thank you.
Yeah. There are downtown Chicago. There's thermal storage in the form of cooling going on. That and there's these 5 plants that are in the blue dots that will chill water down during off-peak energy and be able and hold a lot of that cool water or slurry or whatever it's in the form of, and deliver it to at least 100 buildings downtown. So that's a form of, it's not as advanced as the stuff we just covered with heat, but it's a very simple system. But you probably didn't know about this. McCormick Place is cooled that way. Many other, I don't know what all the other buildings are, but they're this is kind of a way to save energy.
Question.
Okay, sure.
How does this save energy? Are we talking about using heat pumps in reverse, or are we talking about using it directly in air conditioning in the summertime? I'm not
It's
clear.
probably not using heat pumps that I'm aware of. It's probably just using standard refrigeration.
Okay.
But my guess is it's all off peak, because then they can, and they have big reservoirs of this, which keep it from warming up very quickly. I'm thinking.
Would that be substituting for air conditioning then in big business offices directly?
That's, I think some of the buildings are probably set up that way. Yeah, yeah, for AC. I mean, that you multiply 100 buildings plus all that energy, that should make a difference, you would think. But so other places are doing this district cooling as well. I'm just introducing this. This is kind of the flip side of the heat, and just to show you. But so basically, this is my summary slide. We've got a lot of things up here. You may have to grab the slide somewhere, and we're getting blocked. But you know, hydrogen.
It's showing just fine. We can see the whole picture.
You can. Okay, I just can't. I don't see it. Okay. So anyway, you're getting the one thing. Yeah, flow batteries up here, and a lot of storage we just talked about. Of course, pumped hydro is kind of king up there with, and I think on this axis we could start moving into days and weeks up here. You could, if you needed to keep it that long, you'll probably not so much hydrogen, but some of the others you could. But maybe the point is, what I don't see up here is the energy vault, which is the mechanical sky hook thing that lifts the concrete blocks. They don't show it up here, and maybe there's a reason for that. This is kind of interesting, but you still need storage in other places to support the grid. I mean, some of these could still be very useful to have storage, and we'll see.
I like the slide because you have it color coded into mechanical, electrochemical, electrical, hydrogen related, and thermal. That's a very cool slide. Did Argonne prepare that for you? Or
no, it's I did see it before some years back, but this is a more current version of it.
Yeah, very nice.
It's off the internet. Then we're just about done. I just got a couple little things. So basically, this mobile that I had scattered on different slides, you want to keep it balanced, and despite wind blowing it, it getting perturbed in it, and we want it to settle back down. And you can balance things with between baseload and renewables. There's a level there that can be balanced. Some of you want to keep renewables pretty darn low, and maybe we'll find out how that works. Maybe they should be. Then there's load following with baseload that can help balance, and then storage, multiple levels, multiple technologies, and we'll see how these technologies mature. So and how this all works out. It's just kind of an interesting area to me. And just, this is almost my last slide. Bill Gates wrote this book that was released last year, How to Avoid a Climate Disaster. And it's the solutions we have and the breakthroughs we need. Well, it's like a blueprint to get down to zero carbon emissions by 2050. But part of his mission is this breakthrough energy, which is how a philanthropic mission, where he will support energy storage, and he's supported this this ease group in Europe with about $1 billion, I think I heard. He supported some of these other, this Antora is the, that energy, the carbon heat storage using the TPV
Right.
the engine. That was that. But he's trying to plug money into different types of storage. The iron battery, he's supported some of that. But of course, we know he's supported this too. With a how much, Richard? Did he put $1 billion into that and the Natrium? I don't know.
I'm not sure the amount, but Bill has this dream, which I think is a bit unrealistic. He was interviewed about his book a few months after he released it a year ago, and he said at the very end of the talk, "I think we'll get to 85% renewables." And I was shocked to hear him say that. I thought all the way through the book, which I reviewed for this group about what was it, about last fall, I think. And after writing such a meaningful book, I was surprised that he came out with such a high percentage of renewables. I don't know whether he was saying that because he wanted to appeal to listeners or what. We have a powerful question from George in our chat room that relates to this. And I'd like to read it out to everyone and then have you reply. George says, how do we justify investing time and energy into inefficient, intermittent, resource-gobbling, short-lived alternatives like wind and solar and the backup systems that they require, instead of putting the time and effort into highly efficient, 24/7 resource-sipping nuclear power, which the World Health Organization rates #1 for safety? That's George's question. You want to have a go at it?
I don't, part of, there's part of the community, and John Kerry is right up there, who says, we're going to go with the cheapest way to get the efficient, to get the grid up and clean. And that's the only thing I can say with regard to that. Nuclear has to be deployed, and a lot of these new technologies are going to be test beds. They're going to take time. It's unfortunate we didn't do this 20 years ago.
Exactly.
And that's when it should have been done.
Yep.
It should have been done 20 and 30 years ago, and it wasn't.
They were all refused because our democratic society requires that people express themselves, and the people were not educated enough so that the politicians yielded. And I think 20 reactors, if I remember correctly. It might have been more than that. It might have been 200. I'm sorry that I'm forgetting which it was, but there were a lot of reactors were canceled. Some of them partially built over the last part of the last century during the 80s and 90s because of public resistance. And so coming back to what you just mentioned about cost, many of the politicians, I think, are not aware that not only do we have an intermittent problem with renewables, but they don't last all that long, something like 20, 25, maybe 30 years in some cases, whereas nuclear is lasting upwards of 60 years, probably 80 and possibly even 100 years. And so people are not, also, how are you recycling all those wind blades? They're going into landfills. And what about recycling solar panels? We haven't really thought about that in this country. They're doing it in Europe, but not here. And so I think this is leading to political short-sightedness by looking at cost. The politicians are only looking at 5 years out. And in 5 years, renewables look pretty cheap, but they don't think about 80 years or 100 years. And they don't think about the recycling.
DOE usually does life cycle analysis on all this, and I'm not on top of any of that, if they've done it or not done it, but that deals with life cycle analysis, and maybe that's just been deficient in all of this. You know, that's so like the concrete and energy vault. I mean, they need to do a life cycle analysis on our CO2 equivalents to make all this stuff and put it and get it deployed to make it, put it in. What's that going to cost in terms of greenhouse gases? I mean, there's all this stuff that needs to really be done.
That you're right. And I think that this fellow Partinen from Finland has written a book called Climate Gamble, and he's written some updates on that too. But even going back to the Climate Gamble one, which is about 7 years old, it's still a very good book in that it looks into just that thing that you mentioned, the life cycle analysis. And that's a very pertinent way. The politicians should read books like that. Unfortunately, it's not widely read, but it's very pertinent to making these political decisions about what's cheapest in the long run.
Yeah, and that's a good question, you know, but they're trying. I mean, if we wait too long to clean up things, and it's not just the grid, there's other areas to clean up, but time is, the clock's ticking on us too. I mean, I don't know. It's a tough call. Anything else, Richard? Do you have the next one?
There were a couple of comments by Lee, which were pertinent to the remarks that we said about batteries in comparing electric vehicles with hybrid cars. She says, remember, your electric motor is about 95%, your efficiency is about 95% on a Tesla Model 3, while your internal combustion engine is only 20 to 30% for whatever portion of the time you're using it on a hybrid vehicle. And that's a good point.
It is a good point.
The percentage refers to the percent efficiency. That is what portion of the energy is used to move the vehicle forward. Right. The rest is lost as heat from friction, etc. And she also makes the comment about hydrogen, saying hydrogen can cause metal embrittlement, something we don't think about very much before. You've dealt with some of the negatives of hydrogen already very nicely, Lou, but she just adds that one. You're probably aware of hydrogen embrittlement, and that's not a good thing for your storage vessel.
No, I just ran across an article that they developed a real lightweight hydrogen tank that should contain it, but it's not metal. I don't know what it's made. I forget, fiber composite materials or something. But mostly like for airplanes or things like that, and maybe some storage for refueling, whatever. But so there is something out there to replace the metal. That absolutely huge.
Yes, the hydrogen embrittlement I think is mostly of steel. Lee has a couple more points. She says one main engineering problem relating to what you talked about, a block the size of a football field, that you have to heat up to a very high temperature in order to get to radiate heat. And the thermal expansion of the block would be huge if you expanded this thermal cell that you showed. Right. The thermal expansion of the block would be huge, so you'd have to design to accommodate that expansion. Her other comment is that Bill Gates will use his philanthropic energy mission to starve us of energy worldwide by using climate change to justify closing down way too many coal power plants and closing nuclear power plants for other reasons. This is related to his desire for control through the use of smart meters.
Well, can I just say something about the first question we had? First of all, the block isn't as big as a quarter of a football field. The surface area that has to absorb the energy is the area of a quarter of a football field.
Okay.
The block is going to be much smaller, and
okay.
how that all comes together, I have no idea. I'm just throwing it out there.
Sure.
And yeah, you can take the next question, Richard. I don't know how to answer that.
Bill Gates and his philanthropic energy mission. I don't know either. Lee assumes that that Bill Gates is looking for control through the use of smart meters. I have no comment to make. I don't know what his inner thoughts are on that. We'll have to wait and see. But I have to admire the man for some of his points and predictions and insights into the future. But I'm not sure about his desire to control.
Yeah.
Doug Edwards has a comment. He says you would not use just a tank to store hydrogen. An absorbent like a metal organic framework would be included to lower the pressure needed.
I totally agree with that. That
Good.
I had that on my slide, that's the best way to store it.
Good.
Just not just with us. I totally agree with him on that.
Good.
Yeah.
Glad to have you there, Doug. Thank you.
Yeah, it's great. Yeah, I don't know. This experiment with coal, I mean, India and China are just going gangbusters on coal. We'll see how that works out with
I was
you
just
know,
looking at a slide which I will include this fall in a review of a book called "Is Science Enough?" And I found a slide that shows India and China in particular not really getting on the ball in terms of energy conservation, and they're continuing to plan to continue using coal for a long time into the future, and that's sad. Western Europe and the United States is at least trying. Europe more successfully than we are, but trying to get off of fossil fuels,
yeah,
especially France and Sweden, but and Norway and so on. But it's sad to see there's a progression from 2015 to the first half of 2021, I think it is, and it shows very little progress in Asia. So it's interesting for us to look ahead and see what the Western world can do, and we should be doing it because the people in India and China, particularly India, are going to suffer more from climate change probably than we are. But they need to get on the ball too and help the global situation. We're thinking so much from a tribalistic point of view, and we need to start thinking globally.
yeah.
So I want to thank you again for a nice review of batteries. It's a heroic, well, maybe not heroic, but it's a gigantic piece of work, and I do appreciate it, Lou, very much.
Well, I thank everybody who tuned in, and hopefully you can look back at some of the other resources and see the value of storage.
Yeah.
This is the very last slide I had. It's just self-explanatory. I mean, there's lots of pieces to this, and lots of pieces that have yet to be laid down that we don't know, that have to be filled in. So anyway, so this is it.
Well, I'm glad you were an ideal person, I think, to bring us together. And it is an interesting part of the puzzle, very central in many respects. I'm just wanting to make a plug for the fall. I'm hoping to get a tour of I haven't yet got a final answer, but I'm hoping to get a tour of the Holy Wisdom Sanctuary. I think it's not a sanctuary, but anyway, it's out on just north of Lake Mendota, an easy trip that we might make if I can negotiate with them for October the 10th, which I think is our Columbus Day. And I think it would be very nice to take a tour there. We were there about 7 years ago, and it would be nice to go back and see what the results of their architectural advances. It was considered the best lead building built in the Madison area in the last 10 or 20 years. So it should be very interesting to look at. And we will go there physically, and I'll send a report to those of you, including you, Lou, and George up in Minnesota. And people like that are probably too far away to come to that. The rest of the meetings this fall, I think, will be purely a Zoom. I've just really tried the last few times to work out of Oakwood, and at least with my computer, I just find it just too difficult to cope with the hybrid situation that they have, and the attendance there is very low. So I think we may well be back to Zooming. It does contribute to a better, more efficient interaction with people all over the Midwest who want to join us. And we have to spend less fuel driving to Oakwood or any other part of the country to meet in one building. So while it's very nice to have the interchange, it's definitely better than the chat function but at least the chat function does give some opportunity for people to raise comments. I see Lee says it was a super presentation. Thanks. And Bill Timick to everyone says thank you. So people are appreciating it. And I think we'll proceed in this method. My final message out to all of you is I was very pleased by the willingness of the members of this Pathways to a Sustainable Planet group to contribute, including you, Lou, and George, and many others. Let's see, we had Mert Corwin, Lee contributed, Dorothy Boatman, Tony Praza, Doug Edwards, Alan Pentecoff. So we had great contributions, and I hope this will continue in the fall. We can have some repeats from any or all of these speakers and some new people coming in also perhaps to join us in the fall. So please send in your suggestions of titles and perhaps dates that would be most convenient with you. They're all, of course, on Monday mornings at 10 o'clock. And I could put together an agenda. I'm just starting to put it together now. There's a fair amount of freedom and openness. One person suggested the topic of purifying the so-called waste, nuclear waste that we keep calling waste and isn't waste at all. They're simply fission products, and how we could purify those rather than bury them someplace and make them, many of them are very useful medically in both therapy and medical diagnostics. And so we could analyze a little bit what's in the waste. And I was thinking of reviewing a book called How to Drive a Nuclear Reactor. This is written by Colin Tucker from England, who describes how safe and how self-regulating nuclear reactors are, and you can literally take them for a drive. And it shows on the front cover a guy with a steering wheel, and in the center of the steering wheel, where you normally have a hub, he has an atom. And so the idea is how to handle. We think of nuclear reactors as something off in outer space or something that's bound to have green goo flowing from it. If you're forgotten the name of that cartoon guy. Somebody help me.
Dilbert? No, not Dilbert.
Dilbert was good. Dilbert was just fine. He had humor.
Oh, yeah.
The guy with the green goo.
Yeah.
He ran a nuclear plant, and he was
yeah.
behaved like an imbecile. But anyway, he's helped to formulate, I think, a lot of prejudice, anti-nuclear prejudice. But anyway, this book by Colin is complicated in areas, but at least I think it shows very nicely the safety and security of nuclear plants that might be bothering some people. So if we can deal with the safety and security and the waste issues, we might discuss those a bit this fall and make nuclear not such an ominous view for some people who are just learning about it. But there'll be lots of other things, and I welcome all of your input, both to attend and to contribute talks. So wish you a great summer, everyone. And I'll stay in touch from time to time when I see interesting things to share with you. And please feel free to do the same in replies with me. And we can have at least a slow but part-time summertime conversation until we get ready in the fall. Our first talk in the fall will be in I think it's the third week in September. Let me just check here. Yeah, the first talk will be on September the 19th. And so we'll go ahead then. And I'll look forward to seeing you all then. And thanks for all of your participations. I see 3 last things on Bill Timick says, rather than purifying waste, how can we convince regular folk that they are not at all that scary? That's true. We can do that too. And then Simpson, thank you, Bill, was the name of the cartoon. And then Lee makes a final comment. You can help people to know that it's not all that scary by educating children in K-12 grades about it. That's a great idea, Lee. Let me know if you know of any schools that would need some interesting education. I'll try and prepare some slides at that level. I think you may have some, Lou, is that right?
Oh, possibly, yeah.
Did you get down as low as K-12? It was all junior high,
Oh,
right?
well, grade 6 was about as low as
Yeah.
we would go. Grade
So
6,
that's okay.
not below
Well,
that.
I think probably
Yeah.
grade 6 would be as low as one would
Yeah.
want to go.
Yeah.
So, yeah, Lou and I might be able to help Lee in that category. If you have some schools, if you can give us the names of schools who would like people to Zoom in,
Yeah.
we'd be glad to help out. Thank
Yeah.
you all.
Thank you. Thanks,
Have a good
everybody.
one.
Bye.
Bye-bye now.